In this lesson, we will decide when write-allocate with write-back outperforms write-no-allocate with write-through for a store-heavy trace. The trace has 40% store hits and 10% store misses. We assume 64-byte blocks. The write-through cost to level 2 is 8 nanoseconds, and the write-back cost is paid once per dirty block on eviction. We will solve this both mathematically and graphically. First, turn the trace percentages into an average reuse per allocated block. Stores make up 50% of all accesses because 40 plus 10 equals 50. Among stores, the miss rate is 10 divided by 50, which is 20%. That means on average, one allocation serves 5 stores, one miss followed by about 4 hits. We will call that number K equals 5. This bar shows a typical pattern. 1 orange miss that brings the block, then 4 green hits that reuse it. Now, build simple cost models per store. For write-no-allocate with write-through, every store pushes a write to level 2, so the cost per store is 8 nanoseconds. For write-allocate with write-back, you pay once to fill the block on the miss, and once to write back the dirty block on eviction. That is one fill cost plus 8 nanoseconds, spread over K stores. Using K equals 5, the cost per store is open parenthesis T, fill plus 8 close parenthesis divided by 5. We want write-allocate with write-back to be faster, so we require its cost to be less than 8. That means open parenthesis T, fill plus 8, close parenthesis over 5, is less than 8. Multiply both sides by 5 to get T fill plus 8 is less than 40. So T fill is less than 32 nanoseconds. This is our break-even point. If a 64-byte line fill from level 2 is faster than 32 nanoseconds, write-allocate with write-back wins for this trace. Let us see this graphically. On the horizontal axis is T fill in nanoseconds, the time to fetch a 64-byte line from level 2. On the vertical axis is cost per store in nanoseconds. The red horizontal line is write-through at 8 nanoseconds. The green line is write-back, which rises with slope 0.2 as T-fill increases. They cross at T-fill equals 32 nanoseconds, cost equals 8. To the left of 32, green is below red, so write-allocate with write-back is better. To the right, write-no-allocate with write-through is better. As a concrete example, suppose a 64-byte fill takes 16 nanoseconds. Then write-back cost per store is open parenthesis 16 plus 8 close parenthesis over 5 equals 4.8 nanoseconds, which is less than 8. If the fill instead took 40 nanoseconds, the write-back cost per store would be 9.6 nanoseconds, which is more than 8, so write-through would win in that case. In summary, with 40% store hits and 10% store misses, we derived K equals 5 stores per allocated block. The break-even condition is T-fill less than 32 nanoseconds for write-allocate with write-back to outperform write-no-allocate with write-through. Graphically, that is the region where the green line lies below the red constant at 8 nanoseconds.